Welcome to Talking Language AI. This is a series where we host talks and conversations about applied NLP topics, tools, and people. My guest today is one of my NLP heroes, Nils Reimers. Welcome.
Great to be here.
Amazing. Yes. So Nils, I've admired Nils's work for a long time. To give a brief sort of intro and bio, so Nils is currently director and principal scientist of machine learning at Cohere. Previously, he's authored several well-known research papers, including Sentence BERT and the popular Sentence Transformers library. He also worked as a research scientist at HuggingFace, co-founded several web companies, and worked as an AI consultant in the area of investment, banking, media, and Internet of Things. Nils did his PhD and postdoc at the Technical University of, how do you pronounce that?
Darmstadt.
Darmstadt, Germany, in the area of natural language processing under supervision of Professor Irina Gurevich. Again, I'll have you pronounce it. Okay.
Gurevich.
Close enough, at the UKP lab. Super excited to have you, Nils. Thank you so much for coming on. Really excited to sort of learn from your experience, the things that you've been building, and the things that you've been sort of pioneering over the last few years. So thank you so much for coming on. I think I can hand it off to you now. I think you have some slides and we can be sort of going in. Again, to everybody who's joining us now, I would recommend you sign into the Cohere Discord and ask any questions there. I'll be keeping sort of an eye on the thread for questions. And over to you, Nils.
Great. Yeah, high-level presentation on a lot of topics I've been working on in the past 4 years. People that know me, I'm strong on embeddings, so I will present some things, some work on it, why I think embeddings are amazing, what are these, talk a bit more about evaluation and challenges of evaluation, machine learning, and conclude with like what makes an successful open source library and how can you get more stars on GitHub, because that's the currency you want to trade in open source libraries. So first, neural search is a really big hype topic. So over the past few years, we saw like quite a big steep in interest in search, in neural search, which means to use transformer networks, large language networks to improve search results. And an example I show here is like the following. So you take the simple English Wikipedia, just because it's like fewer documents than the full English Wikipedia. And you ask a really simple question: what's the capital of the United States? And if you do this with Elasticsearch, lexical search, BM25, you get the following 3 results. So the first is about capital punishment, because the article about capital punishment contains quite often the word capital and the word United States. Second entry is about Ohio, because Ohio is a state in the United States and it has a capital. And the third entry is about Nevada, because it's also a state in the United States and it has a capital. So from a lexical match, these entries maybe make sense, but from a user perspective, they are really bad. And pretty much every search function, except for maybe Google, Bing, and so on, like really few, are really, really disappointing. So there's like not really any search function I really like. So if I want to find something on Twitter, I often go on Google and search on Google for the tweets I'm looking for, because the search function on Twitter works quite poorly. But luckily now we see a lot of progress in neural search, so that everyone can get like search results which are extremely good. So if you take like a really simple out-of-the-box neural search approach, do the same question: what's the capital of the United States? You get on the first entry the document you're looking for. Washington, D.C. is the capital of the United States. Perfect. That's what I wanted to know. Now, finally, I have a search function that works and which is not Google. which is really great if you want to do search on some internal documentation. Obviously, Google works for web documents, but I can't use Google to search through my presentation, Word documents, emails, and so on. So here it's great that you finally can have these extremely powerful search function on your internal data.
And
one comment.
While on that slide, Nils, so when you say lexical search, that's mainly matching keywords, like the keywords in the query and the keywords in the document. Is there more to it?
Yeah, so that's pretty much matching the words. Then BM25 does a bit more smart matching. So it kind of computes like term frequency and inverse document frequency. So it knows that capital and United States are more relevant than the word the. So it ranks documents with the word capital and United States, or United and States, these are independent words, higher in the results. So that's why we see capital punishment on the top result, because it has the word capital and United States quite often. These words are infrequent, so BM25 thinks these are the relevant hits I want to see.
Awesome, clear, thank you.
So one technique which is really popular in neural search is so-called dense Bi-encoders. Here, the idea is you take the document like the query, you pass it through a transformer network like BERT. BERT gives you contextualized word embeddings, and then you do a pooling operation. For example, you take the mean of all BERT, of all contextualized word embeddings, and this gives you like a fixed size 784 dimensional vector. And then you can search in this. And dense Bi-encoders, they can overcome many problems in lexical search. First, it can overcome the lexical gap. So in lexical search, if I search for what's the capital of the United States, and the article talks about US or USA, it will not have a match between these. Also, lexical search does not respect the word order. So if I search visa, how to get a visa from Germany to Canada, or the opposite, how do I get as Canadian or a visa to Germany, cannot differentiate between these two. And lexical search obviously also doesn't know about related terms. So if I search for Spearman correlation in NumPy, but sadly there is no such function in NumPy, so these dense embedding approaches, they instead can find an entry about how to compute the Spearman correlation in SciPy, because it has learned that SciPy and NumPy are really similar frameworks. Both can be used in Python. They are easily interchangeable. So it can show you the results, even if your search query is not really perfect. And lexical search would just say, hey, there's no Spearman correlation in NumPy, which is not super helpful. So to be really quick, so how to train them? So I could spend like a whole lecture how to train them. You can also find on my YouTube channel a lot of talks where I go more deeper into it. But the idea in general is to have certain pairs, certain positive pairs like A1, P1, A2, P2, and so on. And what these pairs are really depends on your use case. And I will show later an extremely cool application we recently published in terms of classification. So in search, what you often use is you have query answer passages. So what's the capital of the United States? Washington, DC is the capital of the United States. Or maybe you have like some online community, let's say Stack Overflow, and you want to find duplicate questions. So you can say this is a question and that's another duplicate question. Or you work on scientific papers and you say, okay, the paper title and the cited paper title, so one paper cites another, they should be or likely are equivalent on the same topic, so they should also be close in the vector space. And then you train them to push these positive pairs close together. So you say, for example, A1 and P1, that's a query and an answer. These 2 points should be close in the vector space, and all other points should be distant in the vector space. And then you can train this on a lot of data as big as you want. And then you learn these nice vector spaces where the model learns that NumPy and SciPy are similar in meaning. And so you can find related concepts. So big topic in my research was evaluation. So I published a lot of work on new benchmarks, criticizing previous benchmarks. And so I'm really vocal about that. And I really think we think not enough in machine learning about our benchmarks. And that's a big problem because it really stops the progress we're making. So first, why do we need benchmarks? So you can't improve what you don't measure. So that's like an old saying I learned in business administration class. And totally the workflow is the following. So we train a model, we evaluate the model on some benchmark, we get some insights from this benchmark, and this helps us to improve the model. And then we can spin the wheel, and hopefully we get better and better model. And at the end, we want to have like some model or know what is the best model that can solve a given task. In machine learning community and the scientific community, so if you go to any big conferences, NeurIPS or EMLP, what you see is a lot of work where people select a popular benchmark, for example, the Cornell 2003 NER dataset, which has named entities from Wall Street Journal from the 80s and 90s. They check what is the state of the art on this data set. So that's, for example, 94.6. They run a lot of experiments, check did they improve. If they did not improve, they repeat again, and then they improve the performance. So for example, they get like a new state of the art NER system, which has like 94.7 F1 score. They publish a paper, submit it to an EMLP conference and say, hey, this is an amazing paper. You mark your system in bold numbers, and people cheer for your success. But here the question is like, is this model, is this new model, this paper really better? Is it really better than the previous system or older system? And sadly, in most cases, the model is not really better. So it's maybe on par or even weaker. And that's like a big issue because the whole scientific community stalls and does not make any progress. To explain this a bit more intuitive, there's a like nice comic strip from XKCD, so which is like really similar what a lot of people do in machine learning research. Question: do jelly beans cause acne? So that's a question people asked the team, and then so they test the first setting, and they did not find like any link between purple jelly beans and acne. And then they go on, test like the next model. So there's no correlation between acne and brown jelly beans. And they test the next model. So there's no correlation between acne and pink jelly. And they go on and on and on, and they spin this wheel and see, at some point they see, hey, this model, the green jelly beans are linked to acne. And they're like 95% confidence. And there's like only 5% chance of coincidence. If you present it like this, you probably think, yeah, that's bogus research, so that's not proper research. This is just kind of like, it's also called like p-hacking. You test like too much properties, too many settings, and you found like coincidentally some setting where you claim that in this case, green jelly beans are linked to acne, which are obviously not true. So if someone would rerun it, they would find like opposing information. But sadly, a lot of these things happens also in machine learning research. We test all these models, all these modifications, different loss function, different hyperparameters, adding some connections to it, until we come with this green jelly bean, which we say, hey, this is like better on whatever benchmark we're interested in. So what's important to know is that there's a predictive power of a benchmark. So totally what we think is like better on a benchmark, that this is also the better system. So if the benchmark is better on a named entity recognition benchmark, then the system should also be better for named entity recognition. But sadly, what we see over time, that the predictive power decreases. So in the beginning, it's a really good benchmark, and you can say, okay, if a new system is better on this benchmark, then the system is actually better. But over time, as time passes, more and more experiments has been run, more and more things have been published and tested out, the predictive power becomes like smaller and smaller. So at some point, you see some increase on a benchmark, but this has like no meaning if the system is really better. So the chance is like, if you do the benchmark and present the numbers, or if you don't do the benchmark and present the numbers, it doesn't make a difference because the predictive power of the benchmark is like so little. And there's sadly quite many popular benchmarks which has, on my completely unscientific claim, 0 to low predictive power. So for example, Connell from 2003 on named entity recognition, GLUE benchmark, the STS benchmark, MS-Marco for information retrieval, maybe even SuperGLUE, they are become extremely low predictive. So if someone presents like a new state of the art on the GLUE text classification benchmark, I do not really care. And I'm not really convinced that their system is really better for text understanding than previous systems. Sadly, they're still heavily used. So even now, last week at EMLP, you saw a lot of people presenting work, making some improvement, tiny improvement on one of these benchmarks, and say, hey, I got such a great system, which is a lot better for text understanding or whatever you try to solve, which is a really unjustified claim. One benchmark in embeddings that has 0 predictive power is semantic textual similarity, STS. If you look at this benchmark, it's like really, really trivial. So it looks like the following. You have sentence A and sentence B, and then annotators back then from 10 years ago asked people, humans, what is the similarity on this on a scale from 0 to like 5? And then you have like pairs like a plane is taking off and an airplane is taking off. And here you say it has like perfect similarity of 5, or a man is smoking, a man is skating has like a really low similarity of 0.5. And you see many papers in 22 justify state-of-the-art performance of embeddings on STS. But do we really struggle, or do we really expect models to struggle to understand what is a plane and airplane? If you think about, I don't know, most recent ChatGPT demo, it sounds like a joke that people really compare models on can they differentiate and know that plane and airplane is the same. Similar, does an STS score of 76.5 versus 76.8 really make a difference if I apply such a model in a biomedical domain where I want to do want to find information on genes and the potential impact of diabetes? So not really sure if this is like really good predictive power, good predictive benchmark, that the benchmark knows what is a plane and what is an airplane, or playing a large flute or just a flute. And one negative example for me is here, SimCSE paper from the Princeton NLP group. It's a highly cited work, 700 citations. In the abstract, they say SimCSE is a simple constructive learning framework that greatly advances state-of-the-art sentence embeddings. In their evaluation, they mainly used STS data sets, did some comparison to outdated systems, and then many people built on top of their work and proposing better and better SimCSE versions. If you take these models and you run it on like more extensive embedding benchmark, which we recently published, which contains like 58 highly diverse text embedding tasks, you see that the SimCSE system is slightly better than average word embeddings. So average word embeddings is like 10 years old. So got a tiny improvement in the last 10 years. And it's like 10 points worse than the best model at the time of publishing of SimCSE. So here the main issue is that people, or the research group worked on STS data set, got really good results there, but it does not have any predictive power for any more interesting text embedding benchmarks, and how well does it work for other tasks. So that stresses again how critical it is to have good benchmarks that also constantly evolve. So it's not acceptable that we run stuff on 10, 20 years old, but we need constantly new and better benchmarks that are more and more challenging. One benchmark we worked on last year is the BEIR benchmark, benchmarking IR. Before that, a lot of people have been using these embedding approaches to do in-domain information retrieval. So take a model, have training data for it, train the embedding model, and then use it for search. But I found it a lot more interesting to do out-of-domain information retrieval, where you take a pre-trained model and you apply it to some other domain, some other search setting. And in BEIR, we collected a lot of different tasks and data sets. So for example, in tweet retrieval, we have some news article and we want to find tweets talking about this. In Aguan and Touche, we have some arguments and we want to find, for example, counter arguments to it. Fever, we have some claim and we want to find Wikipedia articles supporting or refuting the claim. So we collected a lot of data sets in a lot of different information retrieval settings. And then we were comparing different neural search methods against like a baseline. The baseline is lexical search was BM25. And what we saw, for example, the dense passage retrieval model from Facebook, it only performed well on the one data set on Wikipedia where it was trained, but on all other 17 data sets, it was like weaker than lexical search. And also at that time, the best dense embedding approach, TASB, only was better on 8 out of 18 data sets than lexical search. So this gave like really interesting insights. First, that a lot of these dense embedding approaches have issues for unknown domains. And then a lot of research have been done following up on this. Also that some sparse embedding models like Splate work much better for unknown domains. Also the best approach, BM25, was cross-encoder and doc-defined query, extreme stable and robust across domains. And this gives like new insights, which really leads to like an improvement of the models. So yeah, so that's pretty much what I summarized in the previous slide. So in domain, that's what people did before. We saw dense model work extremely good, so plus 18 points performance, but then out of domain, these dense models work not that well. But recent dense models, they became really strong. So far, the latest numbers I saw is that lexical search is only better on 2 out of 14 data sets. So the authors sadly not evaluated on all data sets. But also here we have to ask again, how good is the predictive power of BEIR? Do people already overfit on the BEIR benchmark? And is it time to move to like BEIR version 2 and find like more and better and more challenging retrieval data sets?
While on that slide, before we move to
sure.
So just to clarify a couple of the ideas here. So one, when we say dense model, so that is, you know, when you create a vector for each document that you're searching, and then you have a whenever you get a query, that you turn that into a vector, and then you do a nearest neighbor. Is that the general sort of definition of dense model that you're using here?
Correct. We project every document and every query to a vector space, and then we look in the vector space, what's the closest document. And we hope that this closest document provides a good answer to the query.
Okay. And then like one of my takeaways, I don't know if that was obvious to people before, is that this, it was probably, I guess to frame it in a question, why was BEIR built so it uses data sets from different domains? Like, was it clear or was it a suspicion that it's challenging for dense retrieval to do this domain adaptation stuff, let you train a model on, I don't know, legal, and then it can't search Wikipedia?
Yeah. So that was not the intuition before. So it was more putting numbers to a feeling. So before, people working in domain, this in domain setting, so this is the MS Marco data set, and say, okay, we train on it, we evaluate on it, and show, okay, we have like extremely high boost in search quality. So 18 points, that's massive. So that's what what you extremely notice, and then people have been extremely vocal about this and say, semantic search with dense embeddings is so great, it works so well. But then you apply it on your data. So you apply it in the legal domain or in biomedical domain or in the fashion domain. And you have the feeling, okay, doesn't look so good. So bio-ask is like question answer retrieval in biomedical domain. As we see, the dense embedding model is much weaker than the lexical search model. So, and this is like just a feeling. So you read all the papers, say, hey, that's amazing, that's a new thing. But why does it not work for your case? And here we put numbers to this feeling and really showed, okay, it's not only you, it's not only your feeling, but yes, the models, they have challenges in out of domain settings. And this insight, putting numbers to it, spin up a lot or inspire a lot of new research, people investigating, okay, why are dense embedding models so strong in domain and so weak out of domain? So one thing people found is like in domain, you have like a really high train test overlap. So most test queries have been seen in training time. And then obviously these learned models work extremely well if they have seen this. Also, people showed like out of domain words, like unseen words, what's the impact that dense model extremely struggle with unseen words. And this gave like a really lot of new insights how to better train these models, like see, okay, how can we create better benchmarks so that the test and train set is really separate? How can we deal with like unknown words and so on?
Okay, and to people who are new to this kind of these kinds of data sets, the documents, are they short enough to fit within, let's say, the token limitation, or are they broken down into smaller chunks? How is that sort of dealt?
Yeah, sadly, that's kind of the limitation of this benchmark. So this is mainly passage retrieval. So the query and the documents, they mainly fit into the context lengths of a transformer network. So like 512 word pieces. There's some data sets like Robusto4, which have like on average like 700 words in a news article. But there's no crazy data set involved where you need to find, I don't know, PDF documents with hundreds of pages. And so that's like still a blind spot where a new, better benchmark could be created.
Okay. And when we say encoders, is the general case here that you have one model, or is it a model for queries and a model for documents, or is it different across different models?
It's different across different models. Like DPR has like two different models, like one for query, one for document. TASB has the same for query and document. And then people also studied this, like new benchmarks also give possibility to study new effects, showing that the same model works better, especially for out of domain words. So if there's like an out of domain word, a word the model has not seen during training, if you have like two different models, they projected to like different points in the vector space, so it will not be found. But if you use the same architecture for this, it still projects it to the same or roughly the same point in the vector space. So that's why same model, encoding model for query and document work totally better, especially like for the out of domain setting.
Awesome. Fantastic. Yeah, you can go ahead. Thank you.
Great. This year, we published the massive text embedding benchmarks, which is kind of like a follow-up work, but more put it a bit more broadly in perspective. So we collected different tasks, like where you can use embedding models. You can use them for clustering. You can use them for bitext mining, meaning finding sentence with the same meaning in different languages. You can use them for retrieval, for semantic textual similarity, for summarization, for text classification, for pair classification, and for re-ranking. And so this is like a project that started also a really long time ago. So when I published the Sentence BERT paper, Sentence Informer papers, It showed good results on STS and Cent-eval, which was like the de facto standard in embedding evaluation. But if you really use it, it didn't perform that well. And also the original Sentence BERT model didn't perform that well as universal sentence encoder, even such that the benchmark on STS showed the opposite. And so over the years, with different help of different people and so on, I collected first internally, like a lot more training data, a lot more data sets to evaluate my models on. And then luckily this year, we have been able to open source this and run a lot of evaluation on this. And here we tested different models on these 58 data sets. What you see on the x-axis is the speed, like how quick is the model. On the y-axis, how good is the model, and then the size of the circles, like how big, how many output dimensions do you have. And yeah, what you totally see is like some cluster around here where people used like BERT-based, like 110 billion parameter models. And then we see like different sizes, like the one model on MPNet and GTR, they perform extremely well. Also here, some mini LM models work really well. And then at the more left side, we have like these massive 6 billion parameter model that show also kind of like a nice improvement. But if you really compare the difference between like this model, so here the center point and the MPNet center point, the difference is not so small, but it's like two magnitudes slower than these smaller models. So I always found like this interesting to find like a model that's not only good, but also really fast. So another interesting application we showed this year is few-shot learning with embedding models. So GPT-3 popularized few-shot learning with prompt and in-context learning. So what OpenAI showed in their paper is that if you want to do sentiment classification, you can create like a prompt like this, describe the sentiment. Then you have some in-context examples. I love this place, which you say it's positive. I don't go here, which is negative. And then you have a new review, great pizza, which you want to classify. And I was never a fan of prompting and in-context learning, because first, it has an extremely high sensitivity to the prompt. So here it can make a difference if you put a colon or an exclamation mark or question mark, which can absolutely change the performance. And so you never know, do I have to put like a colon or a question mark at the end of this? Do I have to have like a new line or not? Also, writing the prompt can be challenging for sentiment classification. It's kind of easy, but if you have like more complex, nuanced tasks, it can be challenging to write the prompt for that. Further challenge is you have limited context length. So the original GPT-3 can do like up to like 2000 word pieces. So if you have like longer examples, like movie reviews, you can only present like 10 training examples. But what happens when you have like 20 training examples or 100 training examples? There's like no way how you can use these in an in-context learning example. And also you have quite high compute overhead. So the encoding time complexity is quadratic with the length of the input. So if you have to provide like all these examples at every call, you have like a lot of compute overhead to it. And Moshe from Intel AI came up with like a really cool idea of few-shot learning without prompts. So he was sitting together on a weekend, played around with sentence transformers on the REF benchmark. There you have like 50 examples on extremely challenging classification tasks from industry. And yeah, he worked on a weekend on this and got a system that was like a little bit better than GPT-3 from 62 to 66. In the most recent version, there was like quite nice big jump of improvement. But this difference in performance is not what excited me. What really excited me is first, the model is like 1,600 times smaller. So SetFit works with like a BERT base model, and you don't need like 175 billion parameter model. Also, the model is around 20,000 times faster, or maybe even more faster than that, 100,000 times faster, because you don't have this in-context examples, which add a lot of compute. You can use it with unlimited number of training examples. So GPT-3, you can only use like 10 training examples. Here, it doesn't matter if you have 10, 20, 100, 1,000, million training examples. You don't need any prompting, which makes it extremely simple. And it works across 100 languages. So in the research of SetFit, we tried to do few-shot classification for Japanese, and we totally failed with these in-context prompt examples. But with embedding approaches, works extremely simple. And how it works. So it works really similar to like these embedding approaches. So here we form again these pairs. In this case, we take a pair that has the same label. For sentiment classification, we say, I love this place and the food is great. And I say, okay, these are two examples that have the same label. They should be close in the vector space. Similar, terrible pizza and horrible service should also be close in the vector space, has the same label. And then everything that has different labels, like I love this place and horrible service, should be distant in the vector space. And then you run on these few examples, like 10 training examples, contrastive training. And this transformed the vector space from something which looks like this, where blue is like negative reviews and orange are positive reviews, to like a really nice separated vector space where you can easily draw like a decision boundary and say, okay, everything to the top bottom left is positive, everything to the top right is a negative, has a negative sentiment.
And just a question on that training process. The starting point here is a BERT model, so like, you know, a pre-trained MLM model that is then goes through this contrastive training.
So in the paper, we found that using a pre-trained sentence transformer model works better. So you first take a sentence transformer model, you train it on like Q&A pairs, like what's the capital of United States? Washington, D.C. is the capital of the United States. And then you run the contrastive training on this.
Okay, and then the sentence transformer was already trained on contrastive training, right? And is there a MLM before that, or is it, you know, from scratch?
Yes. So first you run MLM. So you take, I don't know, BERT base. Then you take BERT base, train it contrastively on some Q&A data. So there's like Q&A data publicly widely available for a lot of things.
And that is to say, if I can just stop you just to clarify that point, because like we had a question on it. So that's, you know, have questions and their answers, and that is to say, okay, the embedding of the question should be close to the embedding of the answer, of its answer, but it also should be far from the answers of other questions. So
correct.
Positive and negative pairs. Okay.
Correct. And then you take this, if you take the model like this, out of the box model, you have these two examples mixed, because for search, you should ignore sentiment. So if I search for what do people think about the new iPhone, I want to find results that have positive and negative sentiment. But now with this contrastive training where you say, I love this place and the food is great, should be close. I love this place and horrible service should be distant in the vector space. You tell, hey, that's what I want to have close and distant in the vector space. And then you get like a really nice vector space like this, where you can train like an easy logistic regression classifier on top of this.
Awesome.
And this works really well. So here we show like number of examples. Orange is like standard fine-tuning as you use it with HuggingFace transformer class, as you have to learn in machine learning. This is the SetFit approach. And as we see here with like 8 training examples, we get already like a really good performance. So the red one is like training on all the training data we have. And here with like 8 examples or 16 examples per class, we get already like a score that's like really, really close. And this gives you like a classifier that works extremely good also if you have like little training data. And there's a cool talk from Lewis on YouTube, just posted a few days ago, where they present like distillation approaches. So you start with an MPNet, which is like a BERT base size model, 100 million parameters. And then they distill it to a mini LM 3-layer network. And as you see, the performance is like roughly the same. So what you get now is like a text classification performance as powerful as GPT-3 with 175 billion parameters, but with a model that has just 20 million parameters, which can easily run on your phone, in your browser, on the edge, and you get the same or better performance. And that's, I don't know, I'm still totally amazed by that you don't need like a compute cluster to run GPT-3 and can still get really good results. So final topic, or second final topic, is like multilingual search. So that's the most recent project I've been working on at Cohere, to work on a multilingual embedding approach. So far, the dominant method in search is like lexical search, BM25. But if you go and have like a multilingual data set, let's say you create like some platform, I don't know, you create Reddit, people post in all types of languages on Reddit or Twitter, and you want to provide like search function for all these languages. It's like really, really ugly to build this. First, you need to do language identification on docs and queries, because every language needs a different tokenizer. So in English, you can just tokenize on white spaces and then index this, but this does not work for Chinese. So for Chinese, you need a different tokenizer than for English, and so on. Also, stop word lists must be different. So in English, you have certain stop words, but these stop words are different for French, German, Chinese, Russian, Turkish, Arabic. Also, what you often do is like stemmer, where you reduce words to the stem, like docs, plural docs goes to doc. And this is also like language specific. So every document has like a different pipeline, different tokenizer, different stop words, different stemmer. For every language, you need a different index. So you have an index with all the Arabic documents, all the Chinese documents, all the English documents. And then if I enter a search query, I first need to know what language is this query in. And this can also be challenging, because there are words which it's like ambiguous. If you take the English word die, in Germany, the word die written the same way as an article. So just from the word, you don't know what's the language, and so you don't know which index do I need to hit. Do I have to search the English index or the German index? So you might need to query like multiple indices. And out-of-the-box systems like Elasticsearch only support few languages, because it's like really, really painful to create these tokenizer stop word stemmer for every language. With multilingual embeddings, it's quite easy. So you take the model, you take the text, pass it through a transformer network, you get an embedding out of it. You don't need to do any language identification. You don't need to have like any stemming, stop words, and so on. So everything can be the same pipeline. But however, there have been previous work on multilingual embeddings, but a big challenge was the lack of training data. So what people did before is they used, from the neural machine translation community, translated sentences and trained models on this, or aligned models, English models on this. But here we see that models only work well on the sentence level. Another line of research is like people use machine translation, like Google Translate, to translate query answer pairs to other languages. But here the models don't learn language and country specific properties. So that people have been using MS Macro, which has like a lot of questions, how to do taxes in the US and how to file certain forms, and then translated this to German. So now the model knows in German how I could file my taxes in the US, but the model has absolutely no idea how to do taxes in Germany and how to file all the forms that's required in Germany to do my taxes. And as mentioned before, models are really bad in out-of-domain settings. So if I hit the model and ask some German-specific question, how do I file taxes, or how do I get a tax refund? The model has like absolutely no idea how to do it and how to learn it. So what we did at Cohere, we say, okay, data is the key. So we collected large quantities of training data, not from machine translation, but actually written by people of that language. So for example, Germans asking questions how to file the taxes in Germany, together with the answers written from Germans, how to do the taxes or how to file certain forms in Germany. And overall, we collected up to like 500 million non-English pairs, which we carefully curated, cleaned, extended, augmented, and so on, which covers like a lot of different topics. And so we hope that the model is like really broadly applicable and can find relevant information across all these languages to minimize the gap we see in these models have on unknown words on unknown domains. And of course, we put it also to a test in different settings. First was like clustering, and search in English, search on non-English languages, and cross-lingual classification, where I have training data just in English, and then want to do classification in other languages. And here the biggest improvement we saw for search in non-English, where previous methods, they all worked like on a sentence level. And here we see like a really big boost of performance on the non-English languages. And one approach which is absolutely amazing with these embedding approaches is like cross-lingual search. So you can type the query in any of the 100 languages. So here it's Arabic. I'm not speaking Arabic. My colleague Amr was so kind to provide this, but he said, it's supposed to ask the question, what's the capital of the United States?
It does.
Yeah, you search the English Wikipedia on this, and obviously Elasticsearch has no idea what this Arabic garbage is. But if you do semantic search, it has like no problem to match this, because this text is matched to a vector. The vector is really close to the English. What is the capital of the United States? And then you get the perfect match to like Washington, D.C. is the capital of the United States. Interesting aspect here is in terms of like language bias if you create these models. So either some models, they have like a strong language bias, meaning they prefer certain language combinations. So for example, if you take the LIBSE model, you see all the Russian points are in the left corner, or the English points are in the right corner. For other models, it's more like mixed together, and there's like no strong separation between languages. And the question is like, is language bias good or not good? So side effects with language bias is that same language results are ranked higher just because of the language. So if I search what's the capital of the United States in Arabic, I preferably find Arabic search results in the multilingual corpus, even such that maybe the English hit is a better answer to my question. But so you could think that a model without language bias is nicer, that it finds you the perfect document, the perfect information without language. But here the challenge becomes in things that are specific to languages, where languages are also really tightly coupled with countries. So for example, if I search in English for wedding in an image search system, I expect some happy picture like this. So, you know, that's the traditional Western picture, how a wedding should look like, the bride in a white dress and the man in a smoking or suit, black suit, white skin. If the model does not know about the language I'm searching in, and I search in the Hindi word for wedding, sadly, I'm not speaking Hindi, but Google Translate told me that's the Hindi word for wedding. And the vector spaces does not have like any information about the language. So it just sees the content in terms of wedding. It will retrieve the same result. And here it's like doubtful if people that search in Hindi for wedding would be really interested to get like a Western picture of a wedding. Presumably such person would be more interested to get like some weddings, how they are typically celebrated in India. Similar, who's the president? Here we assume Joe Biden, links to president. But if you ask in French, who's the president? you're probably not so much interested in the US president, but you're probably more interested in the French president, or maybe, I don't know, you speak, there are a lot more French-speaking countries, maybe you're interested in the president of the respective countries. So there's the question, like, how can you still preserve these country language-specific properties if you don't have a language bias in your model? Okay, coming to the final point, developing open source models, which is also my concluding slide. As you know, I've been developing a lot of open source frameworks over the time. And what I can recommend is to focus on the user experience. So what does your user want to build with your framework? Sadly, you see a lot of open source frameworks that are not built for the user, but maybe just built for the person itself, or built for an experienced user, or just built to reproduce some numbers in a paper. And the test I put out is like, really, okay, I want your framework so simple that you can explain me the framework when we're drunk at a bar with just pen and paper on a beer mat. So can I just bump into you at a bar and ask you, hey, how does this framework works? And that's like my guiding principle. So for example, EasyNMT, it's a framework to do machine translation, which I developed, I don't know, a few years ago to simplify machine translation. It's kind of easy. So first you run pip install EasyNMT, then you do import it, load the model, and you call translate and say, what's the language? And that's pretty much all the code you need. And now you can start to machine translation and do what the user wants, to translate text from one language to another language. Also, you should heavily focus on documentation. I really think that's what successful open source projects sets apart from unsuccessful open source projects. Really focus on documentation. Documentation is way more critical than the code itself and the code architecture, software architecture beneath the library. So really invest heavily on the documentation, and here start easy. So start with an example like this. So here, take a sentence, translate it to German. And then over time, you can build up complexity, say, okay, this is also what you can do, and this is like different sentence splitting and language identification, and so on and so on and so on. But really start easy. Finally, if you want that other people contribute to your open source library, aim for like simple code or software architecture to make it like really simple for people, outside people, to understand your architecture, to contribute to your code. So don't use all the fancy technologies from object-oriented programming with a lot of abstractions and decorator, and spread your code across 1,000 classes. So don't have like really fancy complex software architecture. But I found it really good. If the software architecture is easy, you can just look at the code, see how does it work, even if you're just a beginner in the world of programming. Yeah, that's so much from my side. Thanks for listening, and looking forward to your questions, and also questions from Jay.
Amazing. Thank you so much, Nils. I'd love to remind everybody who is either watching this on YouTube or live, we have the thread in the Discord. That's the right place for questions, and we can, answer them as they come in, and after the session as well. So I'd love to direct you there. Yeah, thank you so much, Nils. That was a great sort of run over, a lot of the different topics that we on this last slide. I'm really curious to hear more from you about your experience sort of running Sentence BERT. So it's this research project and it's code that you've launched, but then it succeeded and it took a life of its own. Curious to hear from you sort of, what are the benefits? What are the insights that you get as let's say, a maintainer of a popular open source package like Sentence Transformers, but also what are the challenges?
Yeah. So yeah, first I would say it's the sentence transformer library is a bit different than to a lot of libraries you see people publish with their code. So often what you see with a lot of frameworks is that they publish the code just with the aim to reproduce the experiments in the paper, to say, okay, this is the table we have, and here's like the few lines of code you can run to reproduce the numbers. But people do not really care about the numbers. So they do not really care about scores on this one benchmark, like blue benchmark. What they care about, like, okay, I want to take this and build my own thing. And here, sentence transformer library is different. You can't take the sentence transformer library to reproduce the results from the sentence BERT. There are like some models available where you can reproduce the numbers, but because it's an actively maintained library, always up to date, also up to date with the newest HuggingFace transformer library, there has been like a lot of changes and you cannot really reproduce the results, but still it's focused on the user experience. So people are not really interested to take this and reproduce this one number in this one table, but they are interested to run it on like topic modeling to see what are the topics in the document. So benefit here is like if you publish the code, there's like not really a way how you can betray. So totally with this jelly beans, you can just run a lot of tests, a lot of ablation, hyperparameter tuning, and then you find like a setting which works well. But if you put out the model so that other people should use it, it has to provide value to them. So if your model just works for this one setting and will not work for anyone else and provides no value for other people, and people will not use it. So my goal was always not to publish a paper and get like this bold line and claim this is a cool new model, but really put out models that are useful and that are easy to use for other people's. Okay. Second insight I get is like a lot of sense from what other challenges people have in the field. So number one question I got a long time is like multilingual embeddings. How can I get embeddings for other languages than English? Where at that, like 2 years ago, I said, okay, there's like no good way how you can get sentence embeddings for other languages. And there are no good models available and methods available. So I started research to do this. Solved this was like a paper presented 2 years ago at NLP on sentence level, not paragraph level. Then second question was like out of domain generalization, like people say, hey, my system doesn't work well for legal domain or fashion industry. What can I do? And so that's where I started the BEIR benchmark, say, okay, first I wanted to have numbers on it and then investigate ways how you can adapt these models to other domains. Challenges is, yeah, it's time consuming. So if you put it out and you interact with the community and answer questions and pull requests and try to troubleshoot things, it takes away time you could spend on like research, creating new papers, building new things. So there you have to find like the right balance for that.
Amazing. That's an incredible answer. And I think this brings us to the end of this conversation. I have a lot more questions. And we have a bunch of questions in the Discord as well that we'll get into. But thank you so much, Nils. Great to have this conversation and sort of learn from you about your work. So thank you everybody for joining us. Thank you, Nils. We'll have links to everything that's mentioned in the Discord and in the description of the YouTube. So all these benchmarks, SetFit, sentence transformers, Sentence BERT, and the Cohere's multilingual model as well.